Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. In this video, we are now at the conclusion state of the family of microwave transistors. So far we have gone through the understanding of the microwave bipolar junction transistor, the heterojunction bipolar junction transistor. Next to that we have the metal to semiconductor field effect transistor, the junction field effect transistor also we have addressed. Then recently we have covered the metal oxide semiconductor field effect transistor here. So the transistors that we have gone through the understanding, now we are concluding how they are useful for the memory devices. Actually our work area is for the microwave engineering. Definitely the power transistors are helpful for the microwave applications, but along with they also have the use into the storage as the memory. So let us see a brief introduction to them and we can go further into the core microwave engineering. So here we start with our topic MOS transistors and memory devices. The MOS here refers to the metal oxide semiconductor field effect transistor. Already I have cleared it into the one of the previous video where we have addressed this particular structure, that the metal for example may be the aluminium, the oxide for example the silicon dioxide SiO2 as the insulating material, and the semiconductor may be either silicon or the germanium. So this type of the structure that has resulted the device metal oxide semiconductor field effect transistor is helpful in many sense. Along with the operating frequency, the higher voltage control range is also there with the power application we have. So now as we have MOS here, we have the types as like the N channel MOS. So N channel metal oxide semiconductor field effect transistor can be abbreviated as NMOS here. Similarly, P channel MOSFET can be abbreviated as PMOS, and the extension to them involving both of NMOS and PMOS here we have complementary. So complementary MOSFET is called as CMOS, and it is very popular to make the memory devices. That is the important one we are going to address in this particular video here. So now NMOS and PMOS along with the CMOS, the abbreviations we shall be addressing throughout this particular video and further here. Now the point is why the CMOS is so popular for the memory devices, because as we go on to the higher frequencies, we know that the power handling capacities along with the device miniaturizations have lowered down, and at such a low level of the power handling capacities, the CMOS offers the lowest dissipation of the power that is not required. So the desired thing is that there should not be any dissipation in terms of the losses we account for. So with the minimum losses, the CMOS technology extends towards the memory devices also. So very first of all, we shall see into the details the schematic diagram with respect to the NMOS here. So here we have the diagram. In this diagram we have a three-dimensional look, the three-dimensional look with respect to the NMOS. So NMOS here stands for the N-channel metal oxide semiconductor field effect transistor here. If you can see the various details into a very tiny portion of the device NMOS here, we can say here this is the high packaging density, and basically when we operate these of the devices into the depletion mode, whatever the terminals we have, the source terminal, the drain terminal and the gate terminal, they are all surrounded by the depletion region, and because of this we have the isolation of the source, gate and the drain terminal in the very tiny portion. Therefore the packaging density offered by these types of the MOSFETs are very popular, those outweighing the performances of the bipolar junction transistor here. So in this diagram you can see the source terminal represented by N positive, that is heavily doped portion here. Now the drain terminal that you can see into the region like the drain here. So here the source, drain and the gate terminal along with the oxide portion here, giving us the EMDA here. So here EM is standing for the enhancement mode device operation here. So the enhancement mode device operation for the A part, here we have extending from this particular region to this particular region, whereas the enhancement mode operation for the device we again have into this particular one. So therefore we can differentiate between the A and B given as the suffixes here. The structure is the same. Here we have N positive, P positive into the channel case, P positive into the channel, then N positive again for the drain portion here, which further is having the contacts made by the metals here. So these are the extensions that we have represented, and this is onto the platform of polysilicon here. Now the enhancement modes that we have represented and the abbreviations as the EMD here, whereas when we have the depletion channel operation, so that time the depletion channel implant for the device operation we abbreviate DMD, depletion mode device operation. So here we have utilized the P substrate here, and inside the P type of the substrate all the other types are by the method of diffusion have been fabricated, and we have all these devices at very tiny level with the advantage of high packaging density here. Now here we shall be going into the more details as far as the performance of the NMOS type of the MOSFETs or the transistors is concerned here. Instead of having the device operation, the performance characteristics we shall be focusing into the more details here. So here for the NMOS type we have the two subcategories here. So the first subcategory we can say this is the N channel corresponding to the NMOS, that it is depletion type MOSFET, whereas here we have the N channel, but here we have the induced type MOSFET. In between the N channel depletion type and that of the induced type, when we see the structural schematics here, the structural schematic is very similar with the only one change with respect to the channel here. So here for the N channel depletion type MOSFET we have the conductive channel. I mentioned here a conductive channel is present in the case of N channel depletion type MOSFET. Here we have the source region, the drain region, the gate region, the corresponding terminals along with the metallic contacts and the ohmic contacts. We have all it is represented that have been grown onto the P type of the substrate. The dimensional lengths have also been represented into the schematic, whereas there it is no channel having the Vg is equal to 0 in the case of induced type of the N channel MOSFET here. The corresponding characteristics can also be plotted here. For the case of depletion type, here we have the IV characteristics taking the Vd, the drain voltage on horizontal axis, and the drain current onto the vertical axis here. So this is the dashed line that is separating the linear region and the saturation region, I can say. So these are the various values that we have obtained for the constant values of the gate potentials here. So here we take VGS, gate to source potential V, that has been greater than 0 here, and when we make it to reduce so that it is into the negative region, that it is VGS is less than 0, we obtain the depletion mode, that is the required here. Whereas for VGS greater than 0, we obtain the enhancement mode of operation for the device here. Similar, we have the plot of the drain current onto the vertical axis and plot of the drain voltage Vd onto the horizontal axis. This is again the dashed line that is quite closer to the vertical axis, separating the linear region and the saturation region here. So here again we have the VGS that is greater than 0. So this is working into the enhancement mode of operation, and this is the line where we have VGS is equal to 0. So this is the operative difference highlighted by the use of the IV characteristic in between the depletion type and the induced type of the NMOS here. Now, as far as the memory devices are concerned that have been fabricated by the use of NMOS, PMOS and further the CMOS here, we show you the simple diagram that has the two input NAND operation, that is the logical operation made possible by the use of NMOSes here. So here I mention two input NAND operation. So as AND operation is the simple bit multiplication here, this is the negation of the AND operation, that you can take it from the digital circuitry here or the digital electronics. So these are the two inputs that we can designate with the capital A and capital B representation here. The dot representation is the simple multiplication of the two, that it is the AND operation, and the negation is represented by bar over it. So whatever the first schematic we have represented, where we have the fabrication of the EMD for the A and EMD for the B. So these are the two MOS transistors that have been used for the purpose of this NAND operation here, and the depletion type mode of the device operation is used for obtaining the output at this particular place here. So this is the another diagram explaining the same things with the schematics shaded corresponding to the different operands or the operative devices involved in the NAND operation here. Whereas this is the schematic of the cross section that you can see. This is the substrate, and these are the various regions that have been formed by the diffusion process, and finally they are operating along with the help of polysilicon and further glass materials here. So in the last schematic we have a logical operation, that it is NAND operation. So when a similar kind of logical operation NOR it is. So NAND, it was the negation of the AND operation and basically the multiplication of the two bits here. Here the OR operation is the bit addition. So the negation of the bit addition is nothing but the NOR operation, and this is made possible with the help of the transistor of NMOS that we have just now seen here. So see here, the two inputs can be given to the gate terminals of the MOS here. So here it is Vi1 the first input and Vi2 the second input, giving response to that of the another gate terminal for the device here. The corresponding potentials for the VDD and VSS can be kept at the highest positive and it can be grounded further, and this is the depletion type, and these are the enhancement type devices or the transistors here, giving us the output at this particular terminal here. Now we extend the knowledge of NMOS and PMOS to see what exactly the complementary type of the metal oxide semiconductor field transistor is. So here we have the diagrams representing. So for part A we have the N tub formed in this particular p type of the substrate that we can see here. So here it is the n positive regions, this is the p positive regions, and in between there it will be the n channel and the corresponding p channel, forming the two field effect transistors. The presence of the oxide and the polysilicon material is there here. Now here in this particular diagram, there it is the formation of the p type of the tub along with the n tub from the previous step here. So this is the B, where we have p tub generated onto the same substrate here. Now in the figure C, you can see here the twin tubs here. So here it is p tub, here it is n tub. The p or n substrate, the polysilicon SiO2 or the SiO2 are represented here. So this is the diagram showing the parts A, B and C corresponding to the various CMOS structures here. The CMOS structures we have shown you. This is the diagram where we can show you in brief how the CMOS operation. So the diagrams are very self-explanatory, where we have the first part, the circuit that has been made possible by the use of n-type and the p-type channels corresponding to the MOS, giving us finally the CMOS operation. So this is the circuit diagram, I can say. The corresponding cross-section diagram is expressed into the second part here. So here we have the two transistors that have been fabricated, we can see into the, along with the help of the p-tub and the further details here. Now here we have the output represented V suffix 0 here corresponding to the input here. So here we can see V0 versus V1, or the Vi also you can take as the input here. And here we have the curvatures corresponding to the current that has been formed with the application of the potentials here. So here I can say this is the current curve here. So this is the CMOS operation brief. So far we have seen the brief introduction to the various types of the MOS transistors here. Now we shall be giving the simple circuitries with respect to the use of these MOS transistors and the available memories today. So here we have the first circuitry, that is a representation of the read-only memory. So the read-only memory is also abbreviated as ROM and called as simply the ROM here. After the ROM, an extension is also available that is called as programmable read-only memory. So the abbreviation is capital PROM here. So this is programmable read-only memory. The another circuitry we see here is nothing but the programmable read-only memory with a facility for erasing the memory content here. So this is called as erasable programmable read-only memory. So the abbreviation here we have EPROM, called as EPROM here. Whereas when the erasing of the memory content into the programmable read-only memory is by the electrical means, here we have the electrically erasable programmable read-only memory, the abbreviation as EEPROM. Next to that, here we have the another type of the memory. So mostly ROM is seen to be the permanent type of the memory storage here, where we have the staticness, we have the random access memory. So this is called as the static random access memory. So this memory is also used into the abbreviation form as RAM, random access memory, RAM here. Now the next circuitry is making the use of bipolarness to the static random access memory. So it is also called as capital BSRAM, bipolar static random access memory. And the last diagram is giving us the circuitry of the dynamic static random access memory, called as capital DRAM. So it is DRAM. The details how the memory stores is a part of digital electronics here. So here our intention was just to see how the MOS transistors that are helpful onto the microwave application are also used for the memory storage here. So here a brief detail with respect to the bipolar type of the static random access memory is given in this particular diagram, where we have the cross coupled type of the PNP load into the left hand side, the corresponding circuitry and the cross section that we have shown in this particular diagram. Whereas for the equivalent circuitry, we have the representation into the right hand side here. The diagrams are very self-explanatory, where we have the P type of substrate and the further details have been diffused inside this particular substrate to have the transistor operation for the memory storage application here. The equivalent circuitry components are represented again into the cross-sectional view in this particular diagram here. Now by the next lecture we shall be addressing the next concluding topic of the chapter here, that it is charge coupled devices. For more details and the knowledge of the microwave engineering, you can subscribe to Ekeeda channel. Thank you.